Hello, everybody. We'll just have folks coming in for the next minute or two. Thanks for joining us. We'll just let a couple more people come in. All right. Thank you for joining us for this webinar today. Before we start, just a couple announcements for our upcoming webinars. On Tuesday, May 14th, we'll have Molly Murphy and Laura Calvimontes Barrientos from Colorado State University, and they'll be presenting an industrial hygiene webinar on building inclusive spaces in the occupational and environmental health sciences profession. Our next Ergonomics webinar will be on Wednesday, May 22nd, and that's with Yushu Yan, who is a PhD candidate at UC Berkeley. And she'll be presenting her research on using wearable devices and deep learning to recognize physical activities at work. You can always find out more about upcoming webinars at coeh@berkeley.edu/about-CE, and I'll post a link in the chat as well. So let's get started. Welcome, everybody. On behalf of education and research centers throughout the country, we are pleased to present the Ergonomics webinar series. This collaborative effort on behalf of each ERC's continuing education program aspires to provide access to current research supported through NIOSH ERC programs. Thank you for joining us. Today's webinar, Occupational Ergonomic Research in the Pacific Northwest, is brought to you by Dr. Jae Kim and the Northwest Center for Occupational Health and Safety. Just a few housekeeping items first. You will be muted during this presentation. If you would like to ask a question, please enter it into the online Q&A box. We'll save time at the end of the presentation to address as many questions as possible. This presentation is being recorded and will be made available on the Center for Occupational and Environmental Health YouTube page within 5 business days. And Dr. Kim has also been gracious enough to share his slides with everybody. I'll provide some more information about that in the chat. All participants who logged in with their registration email for the full live presentation today will receive an email tomorrow with a link to an evaluation form that will qualify participants for a certificate of completion worth 1 continuing education contact hour. Once the evaluation is completed, you will be able to access and print your certificate. We're pleased to welcome our presenter, Dr. Jae Kim. Dr. Kim is an associate professor of environmental and occupational health at Oregon State University. He received his MS in industrial and systems engineering from the University of Wisconsin-Madison and a PhD in ergonomics and biomechanics from the University of Washington. I'll hand it over to you, Dr. Kim. Thank you.
Cool. Thanks so much, Will, for the nice introduction. And again, it's a really great pleasure and honor to be here. And thank you so much for inviting me to the webinar. And today, I'd like to share some thoughts on challenges and opportunities that's happening and arising as time goes. And we'll talk about the occupational ergonomics research here. And I will also showcase what we have been doing in the Pacific Northwest regions, focusing on the state of Oregon. So the first slide is just basically showing the highlights of what's happening in my lab here at OSU. So basically, I would like to pose a questions to you and why, we have been doing this, the research and practice in ergonomics. Why is this important to us and to you? So it could be, I think because it's a webinar, it may be difficult for us to interact, but I think, there could be a number of reasons, but I think I just prioritize, I came up with the short lists and why the ergonomics is important. I think that first of all, as you know, ergonomic injuries or occupational injuries and illnesses pose substantial burdens on our society in various forms. So for the last few decades, maybe more, it's consistently around the 3 million workplace, people, get injured and ill in the United States, which is equivalent to 3 cases per 100 equivalent full-time workers. And the associated annual injury cost of burden in the United States only could be up to $164 billion. We know that much of those costs accounts by the indirect costs that we often not see, right? And so this is the $160 billion. This is heck of a lot of money, but how is the injury burden associated with occupational injuries and illnesses as compared to other significant health conditions? So this is showing annual economic burden of disease and injuries, and the far left side showing the occupational injuries and illnesses, and the darker color represent the injuries that include ergonomic injuries. And we all know that we are afraid of cancer, and we all know that cardiovascular disease accounts, to pose substantial economic burden on our society. Those, circulatory disease, which is cardiovascular related, and the cancer, their the economic burden ranging somewhere between 160 to 170 billion dollars in annual basis, which is very comparable to what we see from occupational injuries and illnesses. This is from the estimate from the NIOSH in 2000. And even compared to the 2020, and that's still, the occupational injuries accounts for a big proportion of injury related burdens in our society, and occupational injury only, its economic burden was about $164 billion in 2020. So we know that this is just highlighting how this is significant in terms of the economic burden on our society. And ever since NIOSH OSHA founded back in early 1970s, and we as a researchers or practitioners, we have done amazing job to reduce this occupational injuries and illnesses. This is showing a non-fatal occupational injuries and illnesses trend over the last 4 decades. And as you can see, back in the 1970s, we have about 9, somewhere between 9 and 10 cases per 100 full-time workers. Now we are down to 3, 3 per 100 full-time workers. So I think this is positive. So then, is this enough? So maybe not. So back in 1992, if we look at this injury trends a little bit closer, on a daily basis, about 13 million people get injured, or ill, and about 6,000 workers die. And about 30 years later, so we still have about 3 million people get injured or ill, and still around the 6,000, 5,500 workers died from work-related injuries. Even though we have done amazing job in reducing these injuries and illnesses, but I think that there's still a lot of rooms for us to improve. And let's take a look at this injury data in different ways. And this is showing the national non-fatal occupational injury rates by states. So now we are in the West Coast, and most of those states in the West Coast, injury rate is higher than the national average, which is indicated by the darker blue, and anything in So Tiffany colors that shows that the state rate is below the national average, and the color in between shows that those states have, for example, Utah and New Mexico and Missouri, Illinois. Those states' injury rates are more compatible to the national average. So the darker gray shows that there's no state stats available for us to present here. So we are in California, Oregon, Washington. We are in the we live in the states where the non-fatal injury rates are higher than national average. And if we look at Oregon, since I am based in Oregon, so this means that 3.6 per 100 full-time employees means that on in every year we have about 62,000 injuries, and every day we have 170 injuries. And during this talk, for an hour talk, we have 21 injuries on average. And as we speak, we have one injury every 3 minutes. So this is again the highlighting, okay, it's economic burdens are substantial. At the same time, number of injury or injury rate seems to be low at the 3.0 per 100 full-time workers, but still, I think we need to do work more to reduce the injuries at the workplaces. I think that's the mission and the reason for existence of the centers like yours. And in addition to this, I think there are many emerging challenges that's happening, and that has happened for the last few decades, and it's continued to be happening, and the new challenges and issues will be emerging. And I would like to ask you, what would be the challenges do you see in the work population? So I think here I'd like to share my three greatest challenges that we are facing in the work population, in my opinion. So usually I would like to get your feedback and the response to the questions, but because of this setup, I will share what I think. I think the aging of the U.S. workforce is a problematic, and I would like, before I talk about why, and I would like to just share some slide here. This is a really nice age distribution back in the 1950s that has a really beautiful bell-shaped. And usually when we define the aging workforce, so it's so we define those folks somewhere between the age of 60 and 65 for elderly workers. So in this red line representing, and it actually divide those working groups between the young and elderly working groups. So as time goes, our age distribution dramatically changing, and this is from 80s, and this is from 90s, and we are going into millennium, and then this is about the 2020, which is now, and this is what's being projected in the 2050. So this is very different from what we have seen from the back in 1950. So we will have proportionally, we'll have a lot more elderly workers, and which is already happening due to the baby boomers are retiring, and sometimes they remain remain in the workplaces after they retire officially. So what does it mean? So I think there are two important the discussion point or challenging point that we are facing here. The one is, as we get aged, as we know as ergonomists, our musculoskeletal systems, they're losing their muscle strength and the bone densities, and we basically lose our physical capability and strengths. Well, whereas our so if we continue to perform what we used to perform, and there will be greater mismatch between our capability versus what the job requires, right? And also, if somebody is, whether somebody, remain in the same occupation for their career, or they, happen to change their career in many different times in their lives, that means that whether you will continue to expose to same exposure for a prolonged period of time, or you may expose to different, types of exposures for a prolonged period of time, that means that you will be exposed to the longer duration of your life in the workplaces. As we know that work-related exposures, and our likelihood of developing the disease or illnesses increases as intensity, duration increases, right? So, in this case, assuming that your intensity of the exposure doesn't change, but basically, the working later in the life will have you to expose to certain exposure or various exposures for the prolonged period of time. That means it's more likely for you to develop or experience, work-related injuries and illnesses. So I think, those are, those two key points are actually, important point and a challenging point for us to, paying attention to address, ergonomic injuries and illnesses, in the workplaces. Another challenging is obesity. So, again, I will show you how our obesity, rate changes over time, and then we'll, go back to why the obesity is problematic at the workplaces in terms of work-related injuries and illnesses. And back in 1985, we were okay, relatively healthy, in terms of obesity. And many of those states didn't even have the records because it was not a societal problem back then. And only, several states, so they have the records. And even so, like obesity rate were like, far less, less than, 10, 14%. But as time goes, the story, changes. As you can see, we are losing more, the wider states here. We started to have newer categories in the 1990s, and this is at the 1997. Let me pause a little bit. And we started to see some of the states have obesity rate of, greater than 20%. And for example, here, Louisiana and some of something called the Stroke Valley, the so-called, and we'll start see dramatic color changes faster than other states. And as time goes, we'll have more yellowish states, where we have obesity rate greater than 20%, and we started to have another category here. The obesity rate becomes greater than 25%, and so after millennium, and we started to see, more states have obesity rate greater than 25%. And now some of those southern states started to have, more than 30%. And it's getting worse and worse. And we started to have another category in 2013, where some of the states are experiencing the obesity rate greater than 35%. And so now the CDC, I think the researchers, we thought that this is too much, and the CDC decided to change the definition or threshold values for, the defining the obesity rate, and so our color scheme will be dramatically changing after 2016. So here we go. So this is what's being presented, after the 2016, because they have changed definition of the obesity, and we have the black, and it looks a little bit better than this one, right? But anyway, so this is a cross-sectional comparisons of the obesity rates at the 4 different time points. And so the long story short, our our nation, the United States, is experiencing higher obesity rates, higher than anybody on Earth. So what does it mean to us as ergonomists? So the first of all, and when we talk about those musculoskeletal injuries or ergonomic injuries, we are talking about the manual motion handling. So when we lift something, and we are not only lifting an object or box, so also we also need to move our mass to perform that work, right? And higher body mass means that there will be greater stress on our musculoskeletal systems, and your muscle needs to exert a lot greater force to counteract the motions and move your body, and that actually creates greater strain on our musculoskeletal system. That's one thing. And the other one is we know that obesity has been associated with various adverse health outcomes that actually increase the risks for the musculoskeletal disorders. So, that's why, and also, if we talk of the ergonomics, right, and, the different body, the mass distributions and different anthropometry means that we need to accommodate those, the emerging populations in the workplaces, and there should be a lot of ergonomic, related anthropometry related changes should be happening in our society at the workplaces. But I don't know if we are doing a good job in actually catching up these obesity rate changes. So I think those are creating also challenges for us as ergonomists. Okay, and another one that we are experiencing it is heat stress and heat related illnesses. And this is, again, I will show you how our, the US annual temperature changes over time. And this first plot shows a US annual temperature compared to, 20th century's average, for example. So this is this particular time span from 1991 to 1930s, and average temperature across this time span compared to the whole 100-year, the average from the 20th century. And anything blue means that this is, at this particular 3 decades time points, average temperature was cooler as compared to the 20th century average. So as you can see, many of those, most part of US, experience colder temperature as compared to a 20th century, average. But as time goes, at this point, our, average temperature between 1991 and 2020, and there is no single state that shows cooler temperature compared to the 20th century's average. What does it mean to ergonomics? So first of all, so we know that heat stress can elevate, the heat cramps and musculoskeletal, strains, and increase the risks for the musculoskeletal injuries. And also it creates a lot of heat-related illnesses at the workplaces, especially for those who work in the outdoor environment, for example, construction workers or ag workers. So these, the global warming and the dramatic temperature rise, posing a substantial, the challenges for us as the ergonomist or occupational health professionals. I think that those are 3 challenges that we are experiencing. So, we have been trying to address some of those challenges that I have discussed here so far. And I'm not saying that we have been addressing all of this, but we are chipping a little bit of this really big gigantic rock and the challenges, to help to address potentially in the near future to reduce, the impact of these 3 challenges in the workplaces, to be able to reduce, work-related injuries and illnesses while we improve the occupational health and well-beings. So for the next, 25, 30 minutes or so, I would like to showcase with what we have been doing, and our lab motto and many of our research projects has approaches from the field to the lab and the lab to the field, and then from the field to the back to the lab. And then we have continuously to have the so basic research work in the lab, but also at the same time we have a really big emphasis on the research translation, so that our work can be the folks at the workplaces can benefit from us. I saw the the raised hand, but I think I was advised to keep continue to my presentation and answer that question at the end. So I'm sorry. I know you have raised your hand for a long time, but just due to the webinar logistics, I will just continue to my presentation. I'm sorry, but I will be happy to answer your question. Thank you for your patience. So As one of the study that we have been doing here at Oregon State is commercial fishing research. And as commercial fishing is one of the most risky industries and really dangerous occupation among all. But at the same time, because of the nature and the environment of the workers at the workplaces, it is difficult for us to do the field-based, observational field-based risk assessment. So that's in part explains why there haven't been much of the research on, objective injury risk estimates. So because of that, we have, worked on using wearable sensors to objectively measure their ergonomic injury risks. And this is one of the example here. And there are two deckhands that's filmed in the actual, working shifts. And these deckhands are actually catching the Dungeness crab, and I think in the month of February. And so as you can see, they are, doing a lot of heavy lifting and repetitive motions in awkward postures in this cold, wet environments. And this particular commercial grade crab pot weighs about 100 pounds empty, but they put weights and baits in it so that this crab pot can sink at the bottom of the flow of the ocean and does not float. So when this crab pot is filled with this the baits, the additional weights, as well as a live crab, and it can weigh as much as somewhere between 300 to 400 pounds. And we all know that NIOSH lifting limits, guide us to not lift something greater than 51 pounds. But this two-person job, their share, one person will handle up to 200 pounds, which is amazingly difficult. So, and we have been using these small wearable sensors, which is called the inertial measurement unit sensors that attach to the chest and upper arms to measure the repetitions and also postures while they're performing this and during their work shifts. And we deploy these sensors to actual fishermen, and these fishermen wore this anywhere between to 7 hours to all the way to a week, set up to 27 hours continuously. We measured that their postures at the 64 hertz, and we summarized this. And then as you can see, and their torso bending was about 17 degrees, ranging anywhere between 5 to 57, and the left and the right arm, their arm raise was about 27 degrees, but ranged from the 8 to 70 degrees, in terms of arm elevations. And this is actual outreach materials that we created to basically visualize the results so that our commercial fishing communities can actually easily grasp what that means for them. And based upon this data, we actually develop a 3D biomechanical model to estimate what would it be to low back injury risk or compression and shear force then apply to the spine. And this is the result, as you can see on the screen, very left bar on the bar chart showing the low back compression at L5 and S1. And as you may know, there are some guidelines and threshold, the values for low back compression force set by NIOSH or ACGIH. And the action limit by NIOSH or ACGIH TLV, they set at 3,400 newtons for low back compressive force. As you can see, all the values, and this the box plot represents this is excuse me, it's not bar chart but the box plot, and this the bottom portion of this bar representing 25th percentile, and the middle bar representing 50th percentile, and at the top of this box representing the 75th percentile. And as you can see, all these boxes outside of the ACGIH TLV or NIOSH action limits of 3,400 newtons. And good proportion of this box plot actually exceeded NIOSH maximal permissible limit, which is 6,400 newtons. And this is showing that during these dangerous craft fishing activities actually poses significant low back injury risks. And the middle box plot shows shear force, and again, good proportion of this box plot exceeded the NIOSH, ACGIH TLV value of 700 newtons. And basically, this shows that the dangerous craft fishing actually is can increase the risks for the low back injuries. And the last box plot shows a low back moment, which median value was about 400 Newton meters, which is very similar to comparable to those ones that we can see the patient handling activities, which is also considered as a really high risks for the low back injuries. And based upon these field-based measures, we also wanted to do more rigorous, the biomechanical, assessments to better understand what would be this, the injury mechanisms. And also, we wanted to also evaluate some of the interventions to mitigate these interventions. While we were actually working in the field for the sensor studies, we found the very brilliant, ergonomic ideas that developed by the fishermen. And this is called, bar, this bar is called Bama bar. That's has added paddings, and they used to stop those sorting tables so that that pot can be tipped and banged against this the bar to release the crab more easily, and also they don't have to bend their back all the way down to the bottom of the table. So we thought that this is brilliant. This control measure can reduce the physical risk factors, for example, low back injury risks. But not all the fishermen use this, and then some of them were skeptical about it. And some of the fishermen and vessel owners asked if we could provide them some scientific evidences so that they can be convinced. So because of that, we wanted to evaluate this. So during simulated crab pot handling activities, we quantify the low back joint moments and then muscle activity, as well as localized exertions. And also we wanted to evaluate this effectiveness of the Bama bar that I just described all there in reducing the risks of musculoskeletal injuries among these dangerous crab fishermen. So in the repeated measures laboratory study, we invited 25 healthy individuals, and their demographic information are summarized on the slide. So basically, they simulated the crab pot handling task with and without Bama bars, and as you can see from the screen in the video. And we had 5 different conditions. The one was control conditions where there's no bar, which is very far left side, and the flat bar was the most common type of a bar in the field. If vessels were equipped with this kind of bar, but the bar configuration was all over the places, and some vessels have a Bama bar but was very low, and some of them were high. But they just set it without any scientific evidences, and they didn't have any ideas, and they just happened to have that kind of bar height. So based upon NIOSH working height recommendations, we wanted to test 3 different heights to see if we can provide them some sort of ergonomic recommendations for these flat bars. And also we found a triangle bar that has similar heights to high bar, but which is presented on the very far right side. And different from the flat bars, the triangle bar, since due to its setup, it only has one point of contact at the bar. So that, basically that one point of contact may provide, some benefit of it. First of all, we thought that, it will be the motion, the banging motion would be synchronous because there's only single point of contact. Also, depending on how they grab this hand, the crab pot, because because of the single point of contact that's away from that's the deckhands, which is right in the middle. So we felt that this can reduce the pinch hazards when they bang these crab pots. So we wanted to evaluate whether triangle bar would be any different from the flat bars. So the flat bar looks like this at above the right upper right corner, and this is a triangle bar just for your information. And this is all the measures that we did. And in order for us to actually, perform the, inverse dynamics in our biomechanical modeling, we actually, modified the commercial grade crab pot to embed the 6 degrees of freedom hand load cell into the crab pot so that we could actually measure, 6 degrees of freedom hand force, measured at 1,000 hertz. And then we feed that into our 3D dynamic the biomechanical model. And also we measured their kinematic data using 3D motion capture systems using those reflected markers. And then we summarize these low back joint moments at the peak, which was summarized by the 5th or 95th percentile values and center tendency as a median values. And also we measured muscle activities during this simulated crab handling activities using electromyography, and then normalize that by the reference voluntary contractions and presented muscle activities at the static, median, and peak, which which were summarized by 10th and 50th and 90th percentile values. Lastly, we also ask, their perceived localized exertion on their low back regions using the Borg CR10 scales, 0 being no exertions and 10 being maximum exertions they can imagine. And this is sort of the result, and this is showing the low back joint moments. And as you can see, the crab pot handling pose substantial moments about the low back, which is 95th percentile values without this Banger bar, which is represented by the darker bar, was about 130 Newton meters in terms of the flexion moments, which is similar to that patient that we can see from patient handling activities in healthcare. And also the lateral bending was substantial, but as you can see, when the Banger bar was installed, in that lateral bending moment substantially decreased, and even further as the Banger bar height increases, as you can see. So we were able to show that the Banger bar was effective mean to reduce this the low back moment, and also that the bar height was an important factor contributing to this reduction of low back moment. And this is low back showing the low back muscle activities. And the crab pot handling activities, again, that requires considerable rectus spinal muscle activities. As you can see, this is almost like more than 150% RVCs. But again, when the Banger bar was introduced or used, the erectile spinal muscle activities substantially decreased, and also as bar height increases, the erectile spinal muscle activities also decreases. And as you can see, there were considerable differences between the right and left erectile spinal muscles. That's because, as you have seen from the video, their the motions while they're doing the crab pot handling, and their motion were unidirectional. It's asymmetric motion, so that's why we saw differences between our right and left erectile spinal muscle activities here. And based upon this, the result, I just shared a few of those highlights, but based upon this, we, created the outreach materials, as you can see on the left side, and show, what, our study was about, how it could help to reduce low back and shoulder injury risks. And some of the fishermen and local fabricators actually reached out to us, from our outreach efforts, and they were fascinated by, our findings, and they asked us if we can provide any the drawings so that they can actually fabricate to install this. And we created the 3D rendering images using the AutoCAD so that they could make this. And this is one example that we created for them to use. And those were sort of our, have been our outreach efforts here. And another one is so using similar approaches. So we have been doing this, the similar research for commercial fishing, commercial timber felling activities, as you can imagine, especially in the Pacific Northwest. And still, while many part of the country's, commercial, timber felling has been mechanized due to the steep terrain in the Pacific Northwest, and there are considerable section of the commercial timber felling has been done manually. So we have been evaluating their injury risks using similar approach. And those are like more or less similar to what what I have presented to you. So basically, based upon the result, we found that the manual timber felling also poses substantial low back injury risks, and therefore we we have been doing the subsequent ergonomic research in the lab settings too. So another one is another field-based studies, we have been using AI and computer vision sensors. And traditionally, we have, as I presented earlier, we have been using motion capture, force plates, and or IMU sensors to evaluate the injury risks, which requires substantial the equipment setup, and also the highly trained, skillful the researchers and practitioners. But what we have been doing in the lab is develop AI-based ergonomic assessment tools for the field studies that people without access to those kind of expensive piece of equipment or extensive biomechanical training can easily use this using these tools. So this is one example that we have been doing with a similar setup. We are using the iPhone camera to replace these expensive motion capture systems to just do the similar 3D biomechanical model to provide the injury estimates. And this has been quite successful, and we our publication is coming up soon. But this is what we have been doing in the lab too. And also, since those sensors have been readily available, again, becoming cheaper and smaller, and we have been developing other sensor network to for hope of prognosis before the injury or illness is already happening. We have been developing this sensor network to using the existing IMU sensors or thermometers, heart rate sensors, and also even the wearable sensor that actually collect the biomarkers to provide workers intuitive feedback on their work exposures, injury risks based upon existing the guidelines to providing them the injury risk. As you can see on the screen, if it is arm elevation greater than 60 degrees for more than 50% of working time, or torso bending greater than 45 degrees more than for a prolonged period of time, based upon heat index or air quality index due to wildfires, we could provide those kind of proactive injury risk estimate to the people who do not necessarily have knowledge on the OSHA regulations or guidelines, so that they can just get some information about their work exposures. And these are something that we have been doing in terms of characterizing ergonomic risk assessments. And for the next few minutes, I'll just show you, our exoskeleton research project that we have been doing in the lab, and we have done so many exoskeleton research in various occupational settings here at OSU, ranging from agriculture, mining to commercial fishing, and healthcare. And this is we called it exoskeletons in the wild, because we not only test this in the lab-based settings, but also we actually test this in the field settings. And some of those research are ongoing. But I think that this some of them are for the constructions, and this is one of the most recent study that we have completed just a month ago, and where we evaluated the passive exoskeletons in the elevated platform that actually is not stable, which is very different from using the exoskeletons in the just base floors. So that's very static. So because we know that exoskeleton may compromise their gaits and balance, so we wanted to see if overhead work in this elevated platform that are not stable will reduce will compromise any posture stability, so that it introduces any fall hazards. So basically, this is the experiment study setup, and then we use three different exoskeletons with the control conditions, and those are all upper extremity exoskeletons that actually support your shoulder while you're performing the upper arm. And this was a study setup, and we basically asked them to pull this cable or wire, and to provide the feedback, so that this pull force was comparable to the actual electricians pulling the wires through the conduit during the construction work, so that they can simulate the simulated work. And we use the 60 degrees of freedom motion platform that actually sway side to side to provide actual mimicking the unstable nature of the scissor lift that we measured. This the sway was based upon the actual field-based measures from the scissor lift, and we measured their posture balance using force plates, and measure their muscular the strain using electromyography, and also we measured their kinematics using the motion captures to understand how this would affect our the musculoskeletal systems. So I think bottom line is here, and as you can see, compared to the control conditions, as you can see here, especially for upper trapezius muscles, an exoskeleton tends to reduce the muscle activities in these the shoulder muscle regions, and that shows the benefit of this. And the other hand, the posture stability, even though some studies have shown that wearing exoskeleton, due to the increase the mass on the upper torso, could shift central mass, overall central mass on the torso, could compromise the posture stability. But I think based upon what we found, the posture stability actually improved with exoskeleton as compared to no exoskeleton condition, which contradicted to our hypothesis. But I think the main explanation here was maybe providing better shoulder stabilization through the exoskeleton may have reduced the posture sway during the overhead work during this lab settings. And that top left one shows the central pressure mean velocity, showing how fast they can move. And that means the lower velocity means greater posture stability. And the right side shows the central pressure root mean square displacement, basically how much you moved, your central pressure, how much it moves. So lower displacement means that it's a greater posture stability. Again, the bottom one is a sway area. So basically, if we just plot all these displacement, create the ellipses, we can create we can calculate the sway area. Again, the smaller sway area indicates a better posture stability. So basically this showing that, that exoskeleton could reduce, shoulder strain while it does not compromise any postural stability. That's what we found here. So I think we have a lot more going on here in the Oregon State, but I think that's due to the interest of time, I will just stop here. But I would like to acknowledge all my staff and collaborators inside and outside OSU, and all the the work and that I presented today. It's was possible because of all the folks that have collaborated, at OSU and different part of countries here. Hopefully, in the future, I will get a chance to collaborate with some of you here in the room, and those the research project that I have presented so far have been funded through various funding agencies, and all the contents that I presented here. It's my and our responsibility of our research groups and co-authors. Does not necessarily represent any official view of our sponsors. So thank you so much, and I think we have plenty of time for questions.
Thank you, Dr. Kim. That was fascinating. We have a couple questions here. I think it'd be great to just have your slides open because some of them relate to the slides. Our first question, this was something I was curious about too. Early on, you had a map of the United States, and it was the non-fatal occupational injury rates by state. And somebody was wondering, they were seeing that there were certain lower rates or there was none listed at all. And for those lower rates, is it because the state isn't reporting those injuries? Or is it kind of a mix? Why is it that certain are lower and certain are higher?
So that's a good question, and I think I don't have a definite answer to that, but basically some of the states they have a more rigorous reporting system than others. For example, I know that Washington, Oregon, California, we are really serious about getting all the injuries recorded as best as possible. So I think in that sense we may have higher injury rates than others, but I think but at the same time I don't want to say that the other states are doing a mediocre job in recording this. So, but I think could it be a really multiple factors? Some states may have more dangerous occupations than others, and some of them they may have more resources to actually run the more rigorous injury surveillance system than others. And I think that's a tough question to answer, but I think that's my 2 cents.
Right, that makes sense. And there's just different factors that go into these numbers. And that answers my question too, which was why on the West Coast are those numbers a lot higher, and it's partly because they're just reporting them more.
Yeah.
Great. My next question was somebody asked about sort of the relationship between providing these tools or studying these tools and acceptance from workplaces and the employers, the workers. How has communication been between, say, the research that you're doing and the employers and industries that you work for? Have they been generally pretty open to these tools? What's that been like in your work?
Yeah, I think that's a very good question. I think that's why I think we put a lot of emphasis on the outreach, and it is I think it's just it's across all the industry that have worked with like transportation, mining, and commercial fishing and forestry, and some of them, especially some frontiers and who are really concerned about their employees' work health and well-beings. And they're really open to those options. And also, even when we used to work, when we worked with the commercial fishermen, some of the fishermen were really brilliant and they're very innovative. And that's how we actually studied one of our innovation studies. The innovation that we tested was actually fisherman developed idea. And And some of the, those, some of those workers and organizations and owners, they are open to the, the changes, and even they suggest and seek for advices. But some they don't, and then some of them, leave us alone. We have done this way for so many generations, and I think, it has worked this way. We don't want any further regulations, and we don't want any changes. But I think, regardless, I think we have just, being trying to reach out, explain what are the potential options. I think our, our philosophy is it is okay for them to not implement those changes, and I don't think it's ever possible. But I think it is important for them to, to aware there are options if they want to, adopt. But I think it is not fair for them to not know what's out there, and just even though they would like to implement some changes, but they can't because they don't know what's out there. And also, for example, for the Bangor bar, some were, curious if it works, we'd like to use it, but we don't see any evidences. And I think that's our job for us to, use this kind of, studies and using outreach materials and efforts for us to share what we know so that they could, benefit from it. But I think that some they don't like, they really like it. They're really supportive, and but the same some don't. I think that's across the boards.
Thank you for that answer. That's really interesting. Another question. Can you explain the reasoning in your research behind choosing passive exoskeletons and not active or hybrid exoskeletons?
Yeah, that's an excellent question. So we always our ultimate goal maybe, unless we'd like to replace humans with robots, I think our ultimate goal may be Iron Man, but I think we are not there yet. So, and as you can imagine, there are only few active exoskeletons available, especially for occupational settings, and oftentimes they are bulkier, and they create a lot of impedance in the movements, and also, could be mobility issues, especially for my applications where, it's including construction, forestry, and commercial fishing. Oftentimes, they need to evacuate the area when they need to, and wearing this heavy, active exoskeletons, they can create a lot of substantial the risks, and at the same time, and I think of practical issue, that's a practical safety issues. But on the other hand, the battery is, it's basically, basically in order for us to move our, entire body mass, we need the big actuators with really high powered, batteries, and may work in very limited settings. But I think we are not there yet. And but passive exoskeletons are far more mature, and many of them are commercially available, lightweight. Most of them are less than 10 pounds. So that's why we have chosen the passive exoskeletons. It's more convenient and more market ready for people to use.
Great. We probably have time for one or two more questions. Somebody was wondering, what program are you using for the AI computer vision analysis in your work?
The program is the program is a computer language, or I don't know if so we are using Python to if that's the question.
Sure, I'm not sure either, but maybe they'll get back to us. But
Yeah,
Python.
and also, yeah, so we use Python, and also, we are, continuously working with OpenCap, the group at Stanford, that who invented, open source AI, machine learning based motion capturing system. They originally developed that for athletics and rehab, applications. But we are currently adopting and modifying that open source, that program for occupational ergonomics and occupational settings.
Got it. Somebody had a comment about the trend in the US and the challenge to workers about providing higher wages when we see that productivity is still increasing, but wages aren't keeping up.
Yeah.
How does that come up in your work? And do you see it as a big challenge for ergonomics and safety?
Yeah, I think that's I love that question, but I don't know if I have a uh, good insights or the expertise to answer that question. But
Yeah,
uh,
it's a big
yeah,
issue, and
yeah, I think that's I think economists or somebody else who actually working on that that aspect may be able to answer the question, but I don't know if I will will be comfortable to answer the question. Sorry.
that's okay, understood. I think that we're at time. Just want to say thank you so much for coming today, everybody. And thank you, Dr. Kim, for this fascinating presentation. Be sure to check out our website for more information and to register for upcoming events. Again, that link will be coeh@berkeley.edu/about-CE. Thank you again for the wonderful questions and participation. I hope everybody has a great day. Thank you so much.
Yeah, thanks so much for having me here, and thanks so much for attending this webinar. It was was an honor to be part of it. Thank you.
Thanks, everybody. Bye.
Bye.